Hi friends, this is Meera. Welcome to Learn Engineering. Today we will solve a problem on sphere. We will find out all the reactions acting on sphere to keep the body in equilibrium. Also, method to draw free body diagram as well as equilibrium equations will be discussed in detail. So let's begin. Let's have a look at the problem statement. In a cardboard box, a football is placed. On this football, a basketball is placed carefully so that after a while none of the balls is moving and they are in a state of equilibrium. Then find out all the reactions to keep the spheres in equilibrium. Radius and weight of football is 10 cm and 5 Newton respectively, and that of basketball is 12 cm and 7 Newton respectively. Length of the carton is 36 cm. Here, none of the sphere is touching the longer side of carton and the basketball is placed such that it remains some distance above the ground. Let's remove one side of box so that we can see the side view clearly. First of all, draw the free body diagram by considering all the forces acting on the balls. There can be three types of forces acting on a body while in equilibrium. One is external force applied. In our case, there is no external force acting on spheres. Second type of force is support reactions. Support reactions act whenever an object is in direct contact to other bodies. In our case, football has point of contact 1 with the vertical side of box, point of contact 2 with the horizontal side, and the basketball is touching the football at point 3. So if any movement of the football is restricted by either box or basketball, reaction will be developed at all these points of contact. So let's find out restricted movement by supports one by one. First of all, consider the vertical side or side wall of the box and ignore other supports. Under application of force, football can freely move in this direction but cannot pass through or push the wall away. Now, this movement is restricted by side wall, so some force will be exerted by sphere on wall, and so reaction of same magnitude as this force but in opposite direction will be developed at point 1. Remember that reaction R1 acts perpendicular to the plane and it passes through the center of gravity of sphere if extended. Now, if only the horizontal plane is there, ball can move in this direction freely but cannot move in vertically downward direction. So reaction R2 will be in opposite upward direction and perpendicular to the plane. Apart from box, the basketball is also in contact to football at point 3. Now, if only basketball is considered while ignoring the box, football is free to move in any direction except this one. So, reaction R3 is in opposite direction and again it will pass through the center of gravity of football if extended. So, these three are support reactions for football. Now, let's talk about reactions acting on basketball. The points where basketball is in direct contact to other bodies are point 3 with the football and point 4 with the vertical side of box. Basketball is not touching the horizontal plane of box, so only two reactions will act. If we do not consider all other supports, the side wall of box restrict movement in this direction and so reaction R4 will act in opposite direction normal to the plane. Similarly, if only football is considered, It is not allowing movement of basketball in this direction, so reaction R3 will be in opposite direction. These two reactions are acting on basketball. One important point is whatever force is applied by football to basketball, force of same magnitude but in opposite direction will be applied by basketball to football according to Newton's third law of motion. So magnitude of reaction force R3 is same for both balls but the directions are opposite. Also, R3 passes through same point of contact 3 and center of gravities of respective spheres. The line of action of R3 is along the line joining center of gravity of both balls, that is AB. So these are the support reactions acting on spheres. Let's free both spheres from all supports and replace the supports by reactions. Now, apart from support reactions, one more force acts on object and that is self-weight. Self-weight of object always acts in vertically downward direction through the center of gravity. So W1 and W2 are weight of football and basketball respectively, and this is the free body diagram of both spheres. Now before calculating reactions, let's find out angles all the forces make with x-axis. In case of football, R1 is acting perpendicular to the wall making 0 degree angle to x-axis. R2 and W1 are acting in vertical direction making 90 degree angle to x-axis. Similarly, for basketball, R4 is acting in horizontal direction and W2 in vertical direction making 0 degree and 90 degree angles respectively. Now rearrange forces so that tail of all the forces meet at center. So drag forces R1, R2 and R3 accordingly. Similarly for basketball, drag R3 and R4. Remember that if you drag or extend force along same line of action, the angle with x-axis will not change. The only data missing is the angle between reaction R3 and x-axis. To find out this angle, we will go back to this point where both spheres are still in contact with each other. First of all, join the centers of gravity of both spheres. R3 acts along this line AB only as we discussed. Now try to make a right angle triangle by extending horizontal or vertical lines from A and B. Here horizontal line is extended from A and vertical line from B and we get a right angle triangle. As R3 makes theta angle to horizontal, this angle is also theta and this is 90 degree. Now if you know length of any two sides of this triangle, you can easily find out theta using trigonometric equations like sin theta or cos theta or tan theta. Let's see how we can find it out. First length we will find is the line joining AB or hypotenuse of triangle. We know that for a sphere, line from center to any point on circumference is equals to radius. So in our case, the hypotenuse is summation of radius of both balls. Radius of football and basketball are given in problem statement, that is 10 centimeter and 12 centimeter respectively. So hypotenuse is 10 plus 12 equals to 22 centimeter. Now let's find out the adjacent side AC. In this case, we can't just add radius of both balls like we did previously, because R1 is okay, but the remaining portion is not equals to R2. R2 is bit longer. So how can we find this length? Here, width of box is given, that is 36 centimeter. So if this width is divided in three parts, first part is center A to box, second is AC, and third is C to box. As balls are touching the side of box, distance from A to box is equals to radius R1. AC we need to find out, and distance C to box is equals to radius R2. So summation of all these sides is equals to 36 centimeter. And we get adjacent side AC equals to 36 minus 10 minus 12 equals to 14 centimeter. Vertical dimension is not given in problem statement, so it would be tedious to find side BC. But we have hypotenuse and adjacent side available, so use equation of cos theta to find angle theta. Cos theta is equals to adjacent side divided by hypotenuse, that is 14 divided by 22, and so theta is equals to 50.48 degree. So this is the angle R3 makes with horizontal for both balls. If we drag force R3 along its line of action, this angle will be theta 2. So if R3 is placed in such a way that its tail is at center, it makes theta equals to 50.48 degree with x-axis. Now let's get back to the free body diagram of both spheres. It is mentioned in the problem statement that the balls are in equilibrium. So either Lami's theorem or equilibrium conditions can be used to solve the problem. Both methods give same result. Here we will find out reactions using equations of equilibrium. If a body is in equilibrium, all the forces are acting in such a way that resultant force R is equals to 0. Thus, the components of resultant force along x-axis and along y-axis are also equals to 0. These two equations are called the equations of equilibrium. Here, x component Rx is summation of horizontal components of all forces. Similarly, Ry is summation of vertical components of all forces. So the first step in this method is to find out x component and y component of each force. Now there are only two equilibrium equations, so only two unknown forces we can find out using these equations. As weight of both spheres W1 and W2 are given in question, football has three unknown forces R1, R2 and R3, while basketball has only two unknown forces R3 and R4. So we will begin with basketball, and once we find out unknown reaction R3, we can use that magnitude for R3 of football, and then there will be only two unknown forces left for football too. So for basketball, this is the free body diagram along x-axis and along y-axis. For convenience, Let's make a table indicating force, its x component and y component in three columns. First force, reaction R3 makes angle theta to x-axis. So x component is R3 cos theta and y component is R3 sin theta. Similarly, reaction R4 acts along negative x-axis making 0 degree angle to x-axis. So x component will be R4 cos 0 equals to R4 and y component is R4 sin 0 equals to 0. Third force is self-weight W2 which is acting in vertically downward direction making 90 degree angle to horizontal. So x component will be W2 cos 90 equals to 0 and y component is W2 sin 90 equals to W2 that is 7 Newton. Now according to equilibrium equations, summation of all horizontal components should be equal to 0. So R3 cos theta minus R4 is equals to 0. Here both components are in same line but are in opposite direction to each other, so they will be subtracted. Similarly, summation of all vertical components is equals to 0. So R3 sin theta minus 7 is equals to 0. Put theta is equals to 50.48 degree and R3 is equals to 9.07 Newton. Put value of R3 in equation 1 and we get R4 is equals to 5.77 Newton. For football, this is the free body diagram along x and y axis. W1 is given, that is 5 Newton, and magnitude of R3 we just calculated, that is 9.07 Newton. So two unknown forces R1 and R2 we need to find out. For this problem, Lami's theorem cannot be used as there are total 4 forces acting on ball and Lami's theorem is applicable if only 3 forces are acting. So only one method can be used and that is equilibrium equations. So first step in this method is to find out x and y component of all forces. Let's once again make the table showing force, x and y components. First force is R1 making 0 degree angle to horizontal. So x component is R1 cos 0 equals to R1 and y component is R1 sin 0 equals to 0. Similarly, reaction R2 acts along y-axis making 90 degree angle to x-axis. And so x component will be 0 and y component is R2. Third force R3 makes angle theta with x-axis. So x component is R3 cos theta and y component is R3 sin theta. Self-weight W1 is acting in vertically downward direction making 90 degree angle to horizontal. So x component will be 0 and y component is equals to W1 that is 5 Newton. Now according to equilibrium equations, summation of all horizontal components should be equals to 0. So R1 minus R3 cos theta is equals to 0. Here both components are collinear but are in opposite direction to each other, so they will be subtracted. Put values of R3 and theta, we get R1 is equals to 5.77 Newton. Similarly, summation of all vertical components is equals to 0. So R2 minus R3 sin theta minus 5 is equals to 0. Again put values of R3 and theta. R2 is equals to 12 Newton.